Welcome back, everybody. Let's take a look at this data that we were looking at in the previous video. And we've got some X and Y information here, and we want to take a look at plotting it. And we're going to start off by just graphing it on a standard X and Y graph. So we go to Insert, and then under Charts, we choose the scatter plot. And I'm just going to use the data dots. Anytime I'm using data, I pretty much stick with dots unless I've got so much that I can't. And you can see the graph here. And if we go back to the Word file, it looks very much like when we plotted it by hand. It's pretty much the same display of information in here. All right, so looks like some sort of an exponential or maybe a polynomial. But we can examine this by doing the same thing we did previously where we graphed it on log paper or semi-log paper. Now in semi-log paper, the y-axis was logarithmic. So what I want to do is I'm going to click over here on the y-axis. And then I do a right click. Oh, that wasn't quite right. I do a right click until I get to Format Plot Area. And then you can see this opens up over here. It's still not quite right. There it is, Format Axis. That's what I'm looking for. And one of my options is a logarithmic scale. So I click on the logarithmic scale and it kind of curves the other way. Well, if I go back to my semi-log graph that I did earlier by hand, you can see that's pretty much the same shape as I am getting here in Excel. Where I ended up with a straight line is when both axes were logarithmic. And so I go to the x-axis, and that's not quite right. Let's try that again. There's Format Axis with a right click. If you're not right on the correct area of the Excel graph, it won't bring up Format Axis. It'll bring up something different. All right, and here's the logarithmic scale. So I make that logarithmic scale, and you can see I have a very nice straight line passing through this data. Okay, that's a pretty good straight line there. And if I click on the data itself and then right click, I can add a trend line. And because it's a straight line in the log-log situation, I know it's a power fit. And so I click on power, and you can see the dashed line is fitting through that data very well. So I'll display the equation and the r-squared value on the chart. And there you have it, 2.2 times x to the 3.3 power. And with an r-squared value of 1, that's pretty close to exact for this data, which is what I was looking for. All right. Now you don't have to be on the log-log chart for this to work. I can highlight this again, and we'll go to Insert, and then Charts, and the scatter plot. And if I click on the data, and then I do a right click on the data, I can add a trend line again. And it's a power fit, we know that now. And I'll display the equation and the r-squared value on the chart. And you can see the dotted line, the little dots pass through the data and give me the same equation as when I did it over here on the log-log plot. So it doesn't have to be a log-log plot for the power fit to work. All right, so there's some good data that fits a power fit really nicely. But now let's take a look at some more data that we're going to fit to curves. And here's some information over here on the tab labeled free fall. And this is the position of an object falling as a function of time. And so basically what happens is an object falls and its position rather is recorded every 60th of a second. And that's what your increments are here. These are all in 60th of a second. And these positions are measured based on the device that you use to record it. So let's go ahead and graph this information. So I highlight everything. And this is good, actually really good experimental data, because you'll see I've got a data point missing here, and that's the the device didn't actually mark the paper at this point. Something weird went on. So you've got some good experimental data. And we go to Insert and Charts, and I'll put the dots in here. So there's our dots. And this is falling under the influence of gravity, so let's highlight the data and fit a trend line. When I go to add a trend line, I know an object that falls under the acceleration due to gravity, its position is going to be a function of t squared. And so it's a polynomial of order 2. You can see the curve fits very nicely. Let's display the equation and the r squared value. And that r squared value is pretty close to 1. I know it says it's equal to 1, but there's always some error in our data. And if you look here, the coefficient of x squared, which in this case would actually be t squared, so you got to be really careful. This by default makes the independent variable x. Anytime you display the trend line, that'll always be the case. But in this example, the x-axis is time, and the y-axis is position, which happens to be labeled x. But in this case, it's actually y. So if I look at this, I get 488.59 as the coefficient of t squared. So 488.59, that's the coefficient of t squared. That's going to equal 1/2 g, the acceleration due to gravity, because this is undergoing free fall. And so if I said, well, let's take 488.59, and I'm going to multiply that by 2. This should be the acceleration due to gravity. And I get 977.18, which is pretty close to the 980 centimeters per second squared, which would be the acceleration due to gravity where this experiment took place. Keep in mind, my x-axis is in centimeters up here and not in meters. And so 9.80 meters per second squared would be 490 centimeters per second squared. So we're pretty close. We're only off by less than 2 centimeters per second squared in that acceleration due to gravity. So that's pretty good data there. All right, well, let's take a look at one more piece of data. So we've got a t squared one here. Let's take another look here at, or let's take a look here at some time versus temperature data. This is actually an experimental situation where we took some boiling water and we pulled it off of the stove, off of the heater in this case, and we measured its temperature every 10 seconds. And so you can see the original temperature is about 94.444 degrees Celsius. Of course, this is limited by the accuracy of the thermometer. In this case, it was a digital thermometer. That's why I have so many decimal places. But I doubt it's quite that accurate, but that's all right. So we want to take a look at the temperature of the water as it cools off as a function of time. And so you can see I've got quite a bit of data in here. All right. And then there's this break in here at 24. I'm going to actually graph all of this data here because I want to show you what's going on. There's some really good experimental stuff happening with this data. So I graph the whole thing here. So I've got it all highlighted. And then I go to Insert and Chart. And you can see that when I choose the dots here, there's so many dots that it just kind of bleeds together. So I'm going to go ahead and choose the line. So what is happening right in here? Well, it's an interesting sort of experimental situation. I'm measuring the temperature of the water as it cools off, and the water's in a beaker, right? And the thermometer is in the water. Well, let's make it more like this. So the probe of the thermometer is down here at the bottom. Well, what happens in this situation is the warm water rises and the cooler water sinks to the bottom. And so what happened here at this point is we stirred the water. And so the water temperature actually rises because the thermometer down here is measuring where it's coolest. Now, it's not really cool. It's still very hot water. But there's hotter water up here at the top. And so when I stir it, the overall water temperature averages out to something larger than the temperature at the bottom previous to the stirring process. And that's what took place here. So if I was doing this experiment correctly, I would be measuring that temperature and stirring the water all at the same time. In fact, we'll look at some data later on that I actually did that. I stirred the water through the entire process. So let's ignore everything past this stir point and let's see what we come up with. All right, so we highlight the data and we're only going to go down until that break. So right about there. And then I go to Insert, Charts. And again, I'll just pull that. And there's the data right there. And you can see all the scragglies in there. That's because it's real data. And let's actually go ahead and move this and make it bigger. And so if I click on the data and then do a right click, I can add a trend line. And let's put in the equation and the intercept, the equation and the R squared value. And there we've got it. And you can see that I have an R squared value of 0.9297, which is actually really good. But clearly this data is not linear, right? That's clearly not linear. So let's change it to something else. We'll try logarithmic. That doesn't look too good, 0.93. You can try a polynomial. That's actually really good, 0.9929. And we'll talk a little bit here about why I can't do that. Power fit doesn't really look too good. And look at that, 0.83 is my R squared value. That's the worst one I've had so far. So then we'll do an exponential, and we can see the exponential fits 0.9939 actually pretty well. Let's talk about the polynomial fit first. And the exponential fit actually is going to have a similar issue. When I look at the polynomial fit, I've got an x squared or a t squared, which means as I examine this curve, if it's a t squared, it's going to eventually go up someplace over here. And that's just not going to happen, right? Think about the situation. You've got water sitting on a table cooling off. This curvature would indicate that at some point in time, the water starts increasing in temperature. And that doesn't make any sense. So we know that's not right. So we're going to throw out the R squared, even though it's really good. But the polynomial, we're going to throw out the polynomial. Let's take a look at the exponential, because in reality, this is also not very good. So this is telling me that the temperature equals 83.507 e to the minus 0.0006 t, where t is time, little t is time, and big T is temperature. You can see I've got not a really very good fit right up in here, but again, that's an exceptional R squared value. But here's the real problem with this. This says that as time goes to infinity, so let's say 24 hours instead of 2400 seconds, in 24 hours, e to the minus 0.006 t is going to be roughly 0, right? As this extends down and down and down, it's going to eventually asymptotically approach temperature equal to 0. But what that means is that the water, as it cools overnight, will become nearly freezing. Well, room temperature is probably 25 degrees, 23 degrees Celsius. And the water's not going to cool off below a room temperature. So the long and the short of it is, even though I've got a really good fit as far as the R squared value, the data does not make sense. And so what we want to do is we want to learn to fit this data to a more realistic curve. And so we're going to do that here in a future video, and we'll take a look at how we actually take that data and fit it to a curve that makes sense. All right, so we'll stop there, and if you have any questions on this information, please leave them in the comments below. Thank you.